This we're going to go through something that's really, really critical for acids and bases, and that's how we can take the concentration of an acid and work out its pH. So we don't need to use an indicator. We can actually do it much more precisely mathematically. So here I've got a couple of examples that I'm going to quickly do the answers for. And I'm going to show you two ways to work it out. Actually, possibly three. So the first one here is a 0.100 mole per litre solution of hydrochloric acid. Hydrochloric acid only has one H plus in its formula. So that means that there's going to be 0.100 moles per litre of H plus ions made when it reacts. Okay? So when it reacts, it'll become 0.10 moles per litre of hydrogen ions and 0.10 moles per litre of chloride ions. These will then attach to the water to become not H plus, but H3O plus, the hydronium ions. Okay? Now, without even having a calculator, I know that this has a pH of 1. Okay? And the reason that I know that is that it's one place, the 1 is only one place away from the units. So it's at the tenths, say that again, it's in the tenths column. Likewise with this one, because the 1 is in the hundredths column, or 2 places away from the decimal point, I know that this is a pH of 2. And the reason that I know that is that I've got one H plus able to be made from HCl, so therefore the concentration of this is also the concentration of my hydronium ions. So if we keep following that same pattern, what would we expect our pH of 0.001 moles per litre of HCl to be? And I'm seeing some hands held up with the number 3, which means people are starting to see the pattern, which is excellent. So the pH of this is 3. Now, so I put X there, I meant to put something else. There's actually a mathematical process for this. And on our calculator we do this. Negative log of whatever our hydronium ion concentration is equals. Now, there's another way that we can write these numbers because sometimes these concentrations get really, really small. So, if we were to try this now with, let's say, our hydronium concentration is going to be 10 times smaller than this. 0.0001 moles per litre. Okay, now we should know what we expect it to be because it's 4 places away from the decimal point, so we expect it to be 4. Let's see if we actually get that in our calculator. And we do, getting a few nods there. So we get our pH of 4. The problem is, we don't always work with concentrations this convenient. Okay, quite often we work with concentrations like 0.2 moles per litre or 0.05 moles per litre or something like that. So the pH is not going to be a nice convenient number. Okay, so there's one thing I did forget. The other way of writing this is now you might be able to see a little pattern between the pH and the way that it's done when I write it in scientific notation. 1.00 times 10 to the negative 4 has a pH of 4. 1 times 10 to the negative 3 has a pH of 3. Guess what this is when I do it in scientific notation? 1 times 10 to the negative 2. So there is a link, and this is what log actually means. Okay, the link between an exponent to the power of and a number like this is sort of our, a number like this for our pH is our link. P actually means, it's a mathematical function, it means negative log of. That's what it means. That's why it's lowercase. Alright, so that's what it actually means. It means it's an inverse scale. So as pH gets bigger, the concentration of hydronium, so the acidity, gets higher. So as this number gets smaller, the acidity gets higher. Okay. So that's what pH really means. So now we're going to have a look at another couple other numbers. Two I mentioned before. Let's say I had 0.250 moles per litre of HCl. And just to show you that it's not just a doubling, let's do twice that. So we go negative log 0.250 equals. If we forget the negative, it makes it a funny number. What do we get there? One decimal place is probably enough. Zero point something, is it? Good? 0.6? Cool. So your pH scale can go below 1. Be aware of that. Okay? If the scale's an inverse type scale, we'd expect this to be about 0.3, wouldn't we? Let's see what it really is. Negative log 0.5 equals, what is it more exactly?
0.301.
Yeah, so it's pretty close to it. So it's about 0.3, okay? So you will find when we do, if we were to make that 1, so double it again, it's not going to be half of that, it's going to be a pH of 0 actually, alright, because 1 is 10 to the power of 0, so you can have a pH of 0. That's all really easy when you've got just one H plus in there. But what if I had something like this? What if I had 0.200 moles per litre of H2SO4? Now that's a little bit trickier. At this level of chemistry, we assume that the acid will fully dissociate. So both of those hydrogen ions will react with water to make hydronium. So the first thing you actually do with this one is do the equation. And you'll notice that 2 hydroniums are made for every 1 sulfuric acid. So if the sulfuric acid has a concentration of 0.2, then the concentration of hydronium must be double that, because there's a 2-to-1 ratio in the equation. Now in reality this is not true, by the way. When you go on to do level 3, you'll see that that's not fully dissociating like that. But for level 2, while we're teaching you the concept, we assume that they fully dissociate. Okay? So this will be 0.400 moles per litre. So the pH of this acid will not be negative log 0.2, it'll be negative log 0.4. So what will the pH of this acid be?
0.379.
Okay, so about 0.4. Fantastic. Okay, so just be aware of that. You do get double the number of hydronium ions, double the concentration of hydronium ions is what is provided by the concentration of the acid. So if it was phosphoric acid, H3PO4, then you'd have to triple it. Okay, so if we had, for example, okay, because one of those makes 3 of those. If this was 0.2, then this would be 0.6. Okay, so just note, before you even do these questions, note how many hydrogens are in the acid first, because that's probably the biggest trap for people. The other thing you have to be able to do is go the other way. So if I said to you that we had a hydrochloric acid, we'll keep it easy, keep it what we call monoprotic, 1 H plus ion. So if I had a pH equal to, let's say, 1.3. Okay? Let's say the pH is 1.3. And it was HCl. You would have to tell me what the concentration of that is. Now this is where it's good to know what a log is. It's also good to sort of click what's the relationship between scientific notation and pH. Okay, so this means, if I have a look at this, if pH of 4 is 1 times 10 to the negative 4, and 3 is 1 times 10 to the negative 3, then this is 1 times 10 to the negative 1.3. That's a bit of a nonsense number. So what we write is 10, put the number 10 in, and you should have a button that is to the power of, so you should have a button that looks like that. If you're working on a computer, I think it's Shift 6 or something like that. 1.3 equals, and you'll get your concentration. Sorry, I forgot the negative. Negative 1.3. Sorry, negative 1.3. Okay, because notice these ones have got the negative in them. So 10 to the power of negative 1.3. 0.05. Okay, so we know that it's 0.050 moles per litre. So we can go both ways. So, in a nutshell, if we want to go from concentration to pH, so I want to find the pH, then I'm going negative log of the hydronium. If I want to go the other way, where I've got the pH, but I want to find the hydronium, then I'm going 10 to the power of the negative pH. So 10, then that little up arrow, or you might have an x to the power of y button. The negative pH equals, and that'll give you hydronium. From what I've seen lately, you're only going to get this for going in reverse will only be for monoprotic acids, so ones which make ones that contain one proton.